Broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and thanks for joining today's webinar. We'll get started on time in 4 minutes. Good morning, everyone, and thanks for joining us for today's webinar entitled Moving Forward with Sensor-Based Nitrogen Management. My name is Anna Goodjohnsdottir, and I'm the project coordinator at the Partnership for Ag Resource Management, who is hosting the webinar this morning. We're joined today by my colleague, Dr. Thomas Green, president and co-founder of the IPM Institute, who will provide a brief introduction. I'm also pleased to welcome our guest speaker. Today, we will hear from Dr. Joshua McGrath, Extension Associate Professor and Soil Management Specialist at the University of Kentucky. At the end of his presentation, we will have approximately 10 minutes of Q&A. So, before we begin, I want to share some brief logistics. You will remain muted as an audience member during the presentations, but please make use of the question box on your screen to type questions for Dr. McGrath during his presentation. I will moderate the questions at the end of his presentation. This webinar is being recorded and will be available later on partnershipfarm.org. By attending the webinar today, you will be eligible for 1.5 CCA continuing education units, 1 for nutrient management and 0.5 for soil and water management. You must be present for the entire webinar to receive these points. If you're watching this webinar live, you will receive an email in the next few hours with the webinar recording, link to submit survey evaluations, and a link to submit your CCA credentials to earn points, if you've not already done so when you initially registered. This form will also need to be filled out if you are attending the webinar over phone. Please note that credits may take a few weeks to appear in your account. If you're watching this on demand at a later date, please be sure to watch the entire presentation through the Citrix platform and not through YouTube to receive credit. A link to register on Citrix will be provided in the text below the YouTube video recording, or it will be emailed to you if you've already registered for this webinar. You are provided instructions at the end of this presentation to submit your credentials. And now with those logistics taken care of, I'll turn it over to Tom.
The Partnership for Ag Resource Management is one of many projects at the IPM Institute, each focused on the power of the marketplace to improve sustainability. Our team of 20 is currently working to increase adoption of best practices and improve outcomes in health, environment, and economics, all key elements of sustainability. As a nonprofit, we work with pest control companies, hospitals, schools, and other facilities and communities, and with food companies and farmers around the world to improve practices and performance and to communicate those benefits to buyers and the public. We write regularly on integrated pest management and other topics for Crops and Soils magazine. You may have seen our article on BT corn last fall. And certified crop advisors can earn a CEU by reading the article and taking the quiz. Next slide. So our objectives with the Partnership for Ag Resource Management project are to identify revenue opportunities for ag retailers that also help keep our valuable ag resources on cropland, to help promote those products and services, and then track sales through annual surveys and estimate reductions in losses of nutrients and other inputs that result from those sales. Then we report those sales data back to our participating ag retailers for their location and also show aggregated data for the state and the region. So we work with ag retailers and industry associations to publicize these great accomplishments through press releases and articles. It's really important to get this news out to address perceptions the public has about agriculture and the role of ag retailers. So our current survey, which is open presently, includes ag retail products and services that address keeping both nitrogen and phosphorus on cropland. After the webinar, you'll receive a survey about the webinar, and that will include links to our products and services survey. One survey is specific to New York, and all other ag retail locations are encouraged to take the Great Lakes Basin-wide survey. These surveys are confidential. We'll share your results only with you and then share aggregated results more broadly across all our respondents. We've had responses from more than 70 ag retail locations to date. So if you've not already participated, please take the time to survey as completely as possible using your best estimates for your acreage covered by the products and services focused on in the survey. So next slide. So as an example, these two photos just show what happens when too much phosphorus gets in the water. These are from Western Lake Erie. The phosphorus feeds the blooms of harmful algae, which close beaches to swimming, make fishing a challenge, and have also shut down public water supplies. The graph on the left shows annual data on the severity of algal blooms since 2002. And we made a lot of progress in the 80s by reducing tillage. But over the last 15 years, these blooms have increased. And this past year was the fourth largest bloom on record. And we know that the agriculture is the primary culprit in this case because of the timing of the phosphorus runoff and the losses. And it's highly dependent on weather, which is why you see the great variability from one year to the next. And we're talking about dissolved reactive phosphorus in this case. Reduced tillage is keeping that particulate phosphorus on the cropland, but we've seen a buildup in the upper layer of soil of dissolved reactive phosphorus, which runs off the surface and also down through tile drains as well. Next slide. Ag retailers have valuable products and services which can keep inputs on cropland and out of waterways. Here are some examples of those that help phosphorus retention and use efficiency, along with some very rough average reductions in phosphorus losses based on published studies. There's lots of variability in the published numbers based on soil type, location, slope, proximity to water, and so forth. But the rough average gives us a sense of where we can make a difference. So cover crops, soil testing, grid or zone sampling, variable rate application, custom application are all revenue generating opportunities for ag retailers that also reduce phosphorus losses. Today, the webinar is focusing on managing nitrogen to both maximize farmer returns and reduce environmental impacts. As I mentioned, our current products and services survey includes questions about your sales of products and services that help reduce nitrogen losses from cropland. Next slide. And ag retailers are making a difference. For example, our annual surveys show large increases in variable rate phosphorus application. In the Sandusky River watershed, those increased from 17% of acres serviced in 2011 to 70% last year, an enormous increase. So using published estimates, the acres of variable rate here alone represent more than 1 million pounds of phosphorus from leaving cropland in that watershed. So we need to track and report on the improvements that we're making so that regulators and the public are aware of the voluntary efforts using the power of the marketplace to drive improvements. So you'll hear from Anna about some additional tools and resources we have for you to use as we work to achieve these goals. With that, I'll turn it back to you, Anna.
So, thanks, Tom. So as Tom mentioned, we do have some free resources available on our website, partnershipfarm.org. On the left, you can see the front page of our newly updated agronomist handbook that's available free for download. The update includes a new introduction and additional fact sheets that you can provide to growers to increase awareness of your products and services that reduce the export of nutrients from cropland. And on the right, you can see the front and back of our phosphorus loss reduction wallet cards, which can be ordered for free on our website as well. These serve as a great conversation starter with your growers, and many people order them to take to their meetings. So to date, we've distributed over 25,000 wallet cards. So our next webinar will occur at the end of June 2018. And you can fill out our evaluation form at the end of this webinar to have the opportunity to put your input on which topic you'd like to hear about. And finally, we'd like to invite you to follow us on Facebook and Twitter for PARM updates and industry news. You can look us up after the webinar on either. So now we'll hear from Dr. Joshua McGrath, Extension Associate Professor and Soil Management Specialist at the University of Kentucky. So.
Hi, thanks, Anna. Let me get the right screen up here. Let me see if I can. Okay, can you see the can you guys see my screen?
It appears black to me.
Okay, let me see something here. How's it look now?
Great. Your presenter view is showing though.
Okay. Let me see what we've got here. Sorry about this.
No problem.
All right, gee. Still, there we go.
It's still showing. Okay.
Yeah, sorry.
That's okay.
I can see where I can change who's looking at it, but I can't change what you're looking at. There we go. All right. How's that? Still the presenter view, waiting for the next screen. All right.
No, it's only the presenter view.
All right. Slideshow. How's that? Still just the, wow, that's weird. Okay. So theoretically, that should be just the slideshow. Let me try one last option. We have 3 options to choose from. Still not doing it. Let me turn off view, slideshow. Don't use presenter view. All right. Okay.
Okay, that's looking better.
All right.
Great. Good to
How
go.
are we now? All right. I had to get rid of the presenter view entirely, so it just wouldn't work on my computer. Things never go as practiced. All right. Let's start over. How's everyone doing? Thanks for having me, Anna. Thanks for the invitation, Tom and IPM. I appreciate this opportunity to talk to you. Hopefully, there's something in here that will interest everyone. Basically, I'm going to try and cover some basics of nitrogen management, how they integrate with more advanced nitrogen management through variable rate nitrogen, and where I think perhaps, I guess my opinion on where we should go with more advanced nitrogen management, integrating multiple levels of technology. So I always like to start with the 4 R's. Put out by the Fertilizer Institute, International Plant Nutrition Institute, supported by the ag fertilizer industry. The 4R approach to nutrient management, as I'm sure many of the people listening in are aware, focuses on applying the right source of fertilizer at the right rate, in the right time, in the right place, in a well-managed cropping system. But I think it's important to point out that right is defined by the performance objective. So oftentimes we forget about this, but the outside ring of the 4R kind of graphic here indicates what the objective is we're trying to achieve. And those objectives can be varied. It can be optimized production or maximizing yield, minimizing environmental impact, maximizing economic return. So any of these are legitimate performance objectives. And so there can be multiple rights depending on what your objective is. So I think there's also a couple of things I kind of like to make sure we're all speaking the same language and are talking about the same thing. And so I like to point out that agronomically small nutrient losses can be environmentally significant. And so oftentimes when I'm talking to ag groups, they say, well, you know, I'm really minimizing my losses, and so I shouldn't carry so much blame for impacting the environment. But very small losses beyond even economic detection by the farmer can be environmentally significant. And likewise, when I speak to environmental groups, they often say, well, you know, when we push for better environmental management of nutrients, it benefits the farmer because they're losing money through those nutrient losses. But that's not always true. Sometimes it is most profitable to lose those nutrients. For example, if I have a dairy farm, it costs me more money to move that manure nutrient source further away so that I don't saturate small areas of the farm. So I can actually lose profitability by protecting the environment. And so we need to recognize from both sides of that debate that it's not a perfect world. There are significant trade-offs involved in managing for environmental protection, and the most profitable system will likely have an environmental impact. Furthermore, we know that maximum yield is not the same as maximum profit. So there's a competing performance objective. If I want to maximize profit, I am not going to be maximizing yield. And nonetheless, it's really just hand waving to talk about what is the optimum rate for yield, for profit, or to protect the environment. Because at the beginning of the season, it is difficult, if not impossible, to determine what the optimum rate actually is for any one of these three performance objectives. So what's the problem with nitrogen? Well, determining nitrogen requirement is complex. Nitrogen requirement to achieve maximum yield for cereal grains is determined by nitrogen responsiveness. So nitrogen responsiveness is how many bushels I get per pound of nitrogen applied. Am I getting 5 bushels for every pound, or am I getting half a bushel for every pound? Nitrogen availability, or basically the soil supply. For example, in a higher organic matter soil, I'm going to have more soil nitrogen available to my crop. And also the way, the placement, the timing, the source of nitrogen that I apply is going to affect the availability from the fertilizer. And finally, potential yield. In a lot of Midwestern states, we've moved away from yield-based nitrogen recommendation systems, but nonetheless, we know that yield is related to nitrogen requirement. It is part of that equation, as we'll discuss a little bit later. What makes it so complex is that all three of these factors, responsiveness, availability, and potential yield, vary in both space and time. So my nitrogen requirement is different every year because my responsiveness changes year to year, my availability changes, and my potential yield changes. And within a field or across field, these three things change. A lot of that temporal component, which is the largest component in variability, is due to weather. So all three factors are independent of each other and independent of time. So this becomes a very complicated equation. Soil type, climate, and previous management vary in space and time and influence yield potential, nitrogen availability, and responsiveness independently. So we have these environmental factors or these human-induced factors that are causing these components of nitrogen requirement to vary. And so I would argue that nitrogen surplus is largely exists due to our recommendations and seasonal and spatial variability requirement. And I think this is an important point. There is obviously a bell curve, a distribution of farmers and how they manage their nitrogen. There are farmers who are way far to the right, extremely progressive, getting very high nitrogen use efficiency, either because they're on good soils, they were just blessed with good soils, or they're really working hard at managing every ounce of nitrogen they put out. And then on the left side of that bell curve, we have farmers that are kind of still doing it the old-fashioned way and perhaps aren't that conscientious. And we have that in every segment of society, this kind of distribution of how conscientious people are. But I think by and large, the middle of that bell curve, the average farmer is doing a very good job, at least to the limit of our technology. There are certainly always ways we can improve, but I think most people are trying to do a good effort. And so when we look at nitrogen surpluses, which are responsible for contributing nitrogen to the Gulf of Mexico, the Chesapeake Bay, or Lake Erie, I think it's largely due to our recommendations and the precision of our recommendations, so that even if you follow the very best recommendations, you are still impacting the environment with nitrogen losses due to surpluses built into those recommendations. So we need to understand why surpluses exist. This is some data. It's getting a little dated, I guess, now from Delaware, some work that we did there where we looked at statewide nutrient balances. This is a very easy thing to do in a state like Delaware. I'm a proud Delaware native, a huge ag state by percentages. It has to be when you talk about a small state like Delaware. So we've got about 450,000 acres of cropland in Delaware. The state is it's just under 1 million acres in Delaware. So it's easy to do this kind of checkbook accounting. And what we did was we calculated two types of checkbook balances for nitrogen on a per acre per year basis. So this is pounds surplus nitrogen per acre per year statewide. We tried to account for all nitrogen inputs. If we look at the management base, this blue line, we looked at manure, fertilizer inputs, and we looked at what the recommendation was for the university. So we took the total acres of each crop grown in the state. We took those acres and applied the average university recommendation. And then we took data on fertilizer sales and manure production, and we said, are farmers applying near university recommendations? And what we found, this is about the time that laws were passed to protect the inland bays and the Chesapeake Bay, and we see a big decrease in surplus nitrogen applied relative to recommended rate applied. Now you see there's still a surplus at the end, and that's because our methods didn't allow us to account for plant available N. So when farmers are recommended a manure rate, poultry litter being the dominant manure in Delaware, they're supposed to use a plant available nitrogen number, which is about half roughly of the total nitrogen in the manure. We use total nitrogen in this calculation, so we expect to see a surplus. In fact, if we adjust for total versus plant available nitrogen and manure, at the end of this time period, we find that farmers are generally applying at the recommended rate. So farmers are following our recommendations. But what we see with this green line is nitrogen in and out. So this is not, we don't subtract the recommendation from what was applied. In this case, we're subtracting crop removal from what was applied. And on the input side, we are now also including average nitrogen fixed by legume crops like soybeans. And we see a very different story. We see that even though the management balance has come into balance and farmers are applying to recommendation, we still see big swings in surpluses that are due to climate. So 2002 was a dry year. 2005 was a dry year. 2004 was a high yielding year, so that surplus came way down. So we see these annual surpluses that aren't addressed by current recommendations or even cover crops. We view cover crops as one of the best management practices available to limit nitrogen loss. And certainly a large amount of the nitrogen loss is through groundwater, that period of groundwater recharge in the fall, winter, and early spring when crops aren't growing. And cover crops act as a catch. But if year in and year out you are applying in surplus of crop removal, cover crops can't capture all of that. At some point, the system still has to leak nitrogen. So while they're an important component of the overall strategy, I think the strategy has to focus on better recommendations to address the surplus issue and relieve that surplus. One of the things that occurred in Delaware as a result of this research was that they decided to invest in irrigation, because irrigation took some of that climate variability out and helped farmers to better predict what the actual nitrogen requirement was and limit that surplus in dry years. That would be difficult in some states where irrigation water is not as amply available as in Delaware. So at this point, I think it's important to talk about accuracy versus precision so that we're on the same page. This is just a graphic from Wikipedia, and it shows two different bullseyes. In this bullseye, we were highly precise, but our accuracy suffered. So we weren't hitting the mark, but we grouped our shots well. Over here, we show low precision and high accuracy. On average, it's a bullseye. But every single point we were wrong. And this is how our nutrient management currently is set up. This is the way nutrient management works, whether for phosphorus or potassium or what we're talking about this morning with nitrogen. Our recommendations are actually, people sometimes say we need more accurate nutrient recommendations. That is not true. Our recommendations are fairly accurate. We need to increase their precision. Our nitrogen recommendations, I'm going to make the argument, are on average right across all the fields, across all the years, regardless of what system you employ. But in every field and every spot in that field, you're probably missing the mark. Here's some data from a friend of mine in Maryland, Bob Cradaville. And so this is just an example to show what can happen and why precision matters. So he's got 3 different field sites spread across the state, did nitrogen response trials. And we see kind of a typical nitrogen response curve at these 2 sites called Beltsville and Y. But at Keedysville, we see something that really fascinates me as a nitrogen researcher. The yields were about 215 bushels per acre with no nitrogen applied. And so it begs the question, where did the nitrogen come from? Well, it came from soil organic matter, but these sorts of things are hard to predict. I believe at this site, when they went looking for a cause, many years, 18 years prior to this, there had been some manure applied to the field, but none recently. In 2008, there was a climate event where we had really warm weather the weekend before Memorial Day, over 100 degrees for 3 days in a row, and a very wet spring. And so we had a very old historic manure application, almost 20 years old, early warm weather to spark nitrogen mineralization very early in the season, so it was available by the rapid growth period for the corn, and plenty of soil moisture to further increase that mineralization. And so at that site in that year, the right nitrogen rate to maximize yield was 0 pounds per acre. But we can't predict this at the beginning of the season. We see this quite often in drought years. A lot of times farmers are very skeptical, and I tell them there are situations where we can maximize yield without nitrogen. As a matter of fact, I had a guy once, he didn't even let me finish my sentence, and he kind of stormed out of the room. He says, McGrath, you're saying we don't need nitrogen. He's like the rest of these environmentalists coming down on us, and he didn't listen to the whole story, because in a drought year, also, our nitrogen requirement is much lower, because I can grow 40, 50 bushels of corn without nitrogen in a dry year. So we see this quite frequently, but it's hard to predict. So we'll take data like that and we'll model it to get nitrogen rate recommendations. So we've got these 3 sites, and these bars are standard deviation. That represents the standard deviation of those 3 data points from the 3 sites. And those bars, that standard deviation is a measure of precision, okay? And one thing that we see is even with the non-responsive site, or especially with the non-responsive site included, our precision increases in hitting the right rate using the average. So that average is accurate. This shows the precision, or how far off we are from the target. And we see that our precision increases with higher nitrogen rates. Let's keep this in mind for discussion later. Typically, we remove non-responsive sites when we're trying to do nitrogen modeling to create a recommendation, because we say, well, if we include that non-responsive site, our recommended rate is going to move lower, and we're going to really short the farmers who have a more, typical situation where you lose yield if you don't have nitrogen. And so we're just going to, basically, this field's on its own. We can't include it in the model because it's not responsive. And so this is how nitrogen recommendations are built. We do many years of research on many fields, and we create this line that predicts the average yield response to these different nitrogen rates. And we can get a line that defines that yield response. If the yields on that vertical axis is Y, and nitrogen rate on the horizontal axis is X. And so for any given nitrogen rate, I can take 100 pounds per acre, plug it in for X, solve for Y, and get the predicted yield. In this case, looks like it would be around 130 or 40 bushels per acre if I only applied 100 pounds per acre of nitrogen. And so this is how we build nitrogen recommendations. Again, even when we drop the non-responsive site, we see that our precision increases as our nitrogen rate increases. So we take this model. Here I've taken the two-site nitrogen production function. Again, yields on the vertical axis, nitrogen rate on the x-axis. I have my equation that I just regressed using, a spreadsheet calculator like Excel. I'm not going to get lost in the weeds and doing first-order derivatives or anything like that, but we do a derivative of that function. And so the derivative just tells us the change in y, so the change in yield for the change in x. So how much yield am I getting for every increase in unit of nitrogen added? So I take a derivative to figure out this change in yield for change in x. Down here at very low nitrogen rates, I have a very large response to nitrogen. So this is called a diminishing return function. We've plotted it as a quadratic. It's a diminishing return function, which means my return yield on investment, nitrogen, diminishes as I increase the nitrogen rate. At some point, my last unit of nitrogen will give me yield, but it won't pay for itself. I don't get enough yield to pay for that last unit of nitrogen. So that's a diminishing return function. In this case, we say, when does my change in yield equal 0? So I've maximized yield increase, and that occurs in this situation when nitrogen rate is 224 pounds per acre and yield is 163 bushels per acre. So that's my max yield. Change in yield now equals 0 for any unit increase in nitrogen. And then I can also look at the most profitable rate. In this case, I used a price ratio of grain to nitrogen of 0.1. So something like $4 per bushel corn for 40-cent nitrogen, or $3 corn for 30-cent nitrogen. Nitrogen to corn grain ratio tends to stay in this range around 0.1, so I just use that ratio. And now instead of solving for 0, where the yield increase is equal to 0, so I've maximized yield, now I'm looking for where that change in yield for the change in x is equal to that price ratio, and that's the most profitable point where the last unit paid for itself. In this case, I'm applying 25 pounds less nitrogen, 199 pounds per acre of nitrogen, but I'm only suffering 1 bushel yield. So you can see that, at most price to grain ratios, 25 extra pounds of nitrogen for 1 bushel wouldn't pay for itself. So it makes sense. It's not much of a yield hit, only 1 bushel. So max yield doesn't equal max money. But it can get more complicated than that. In this situation, we're going to look at the environmental impact. So this is different yield response data, but I'm going to do the same thing with it. Here I've got the yield on the vertical axis again in bushels per acre, the nitrogen rate on the horizontal axis in pounds per acre. But on that secondary vertical axis, I'm looking at soil nitrate down to a 1 meter depth. So they went out, Dr. Cole in Maryland took a 1 meter soil sample, looked at soil nitrate in pounds per acre in the top meter. And what we see a typical quadratic yield response function. That is the economic optimum nitrogen rate with that 1.1 ratio. And there is your soil nitrate curve. So soil nitrate really begins to increase. This is post-harvest soil nitrate, right around that optimum nitrogen rate. So the economic optimum rate in this case was 205 pounds per acre of nitrogen, yielding 173 bushels per acre. The max yield was 174 bushels per acre at 230 pounds of nitrogen per acre. So it's interesting to note that we have this kind of exponential growth function in nitrate loss. So we're going to assume what's in the top meter after harvest. If we don't plant a cover crop, most of that can be lost to groundwater or downstream somewhere. And so even at the economic optimum, it's obvious that we're above background. This is background nitrate loss, right? So it starts to really climb. And the environment is very sensitive to small losses of nutrients. Again, there is a disconnect between the amount of nitrogen that's important to a farmer economically and the amount of nitrogen that's important to a water body. And so small levels of nitrate loss can have a big impact. And in this situation, if we were off the mark by just 1 bushel, 25 pounds of extra nitrogen to get that 1 bushel. Let's assume at the beginning of the season we knew exactly how to maximize yield. The change in environmental impact would be 17 pounds per acre of nitrate nitrogen. That's a huge change. It's not the total 25 pounds that was applied. Obviously, some of that got attenuated in the system, but 17 pounds is pretty impactful. And that's just for a 1 bushel change. So all of a sudden, it becomes apparent that precision in getting the right nitrogen rate is extremely important to the environment, because plus or minus $1 or $2 of profit to the farmer, which the farmer wouldn't even know whether they lost $1 per acre, you know, there's no way to tell unless they had strip plots in there, would mean a big difference economically, because $1 loss would bring you out here, or environmentally would bring you way out this nitrogen loss curve. Here's some on-farm data from Kentucky to further go back to this point about precision. Here we had 4 nitrogen rates. Statistically, there was no difference between the 3 higher nitrogen rates. These are side dress rates that we did in big strip trials on the farm. So the statistics tell us the right rate was down here, because it's no different than up here, although we see a slight yield difference, but it wasn't statistical, between about 190 bushels and 195 bushels, let's say. But there was a difference in precision, because notice how tightly, when I applied too much nitrogen, I mean, truly this was too much nitrogen, all of a sudden I start to group my points. And so when we do traditional statistics, we're looking at the accuracy, and we're trying within a certain limit of acceptable precision to find that optimum rate that's not different than up here. And so we would have much less nitrogen loss in the environment. On average, we'd have the same yield, but we're offsetting risk with this higher rate, because what if these points aren't just background noise? Statistics tells us that these flyers that are above or below that mean line are just noise. But what if they're not? What if this plot actually had a higher nitrogen requirement, or this plot had a higher nitrogen requirement? By actually putting on an excessive rate, we bring those other plots in closer to the mean response. And so in effect, when we look at risk assessment of nitrogen application, economically, the right rate is above the economic optimum rate in any one year, because if I apply 30 pounds of nitrogen beyond the average economic optimum nitrogen rate, 30 pounds surplus, it's going to take these flyers out over the years, and I won't miss really good years where I have good opportunity to make profit. So the right economic rate is even higher than this point. It's 30 pounds up here, which is significantly impactful to the environment. So this brings me back to my point that economic performance objectives are in direct conflict with environmental performance objectives unless we can change the system we use to make nitrogen recommendations. We're at our current limit of technology to protect the environment and be profitable. So this is where I start actually talking about nitrogen models, but I'm going to talk about one from the 1970s. Stanford's equation was an early nitrogen model, and it's what most of our nitrogen recommendation systems are based off of. I have to acknowledge Doug Beagle from Penn State and Scott Merrill from the IPNI. They presented a lot of this at an ASA, Agronomy Society of America symposium a few years ago, and so I borrowed from some of their presentation. So the nitrogen cycle, if fertilizer nitrogen went straight to the crop, then life would be grand, right? So if we applied fertilizer and the crop just took it up and it was a 1-to-1, then, you know, everything would be very easy, because all we'd have to know is what's the yield of the crop, because then we could back calculate how much nitrogen it needed to fill that yield. However, that nitrogen has to pass through the nitrogen cycle gauntlet, which has a lot of microbially mediated processes, which means the weather has a big impact. It goes through forms that can be lost very easily. Nitrate nitrogen can be leached. It can be denitrified if the soil is wet. If we surface apply fertilizer or manure, we have volatilization of ammonia. So this nitrogen cycle starts to complicate matters. So this is some data from Penn State from Dr. Fox, and he showed that total nitrogen uptake on the vertical axis here is linearly related to total yield. And this is simple to understand, that there's a certain amount of nitrogen, a percentage of nitrogen typically in grain that we're harvesting. And so as we harvest more grain, we're taking more nitrogen out of the field. But why doesn't this figure on the right look the same? The economic optimum nitrogen rate is not linearly related to yield, now shown again on the horizontal axis, but now on the vertical axis we have the economic optimum nitrogen rate. If it wasn't for the soil nitrogen cycle and climatic variability in how we apply our fertilizer, the figure on the right should look like the figure on the left, that as yield goes up in a field, the proper rate should be linearly related, but it's not because of the nitrogen cycle. Soil nitrogen supply varies because of the site characteristics, soil type, slope, all of those things, texture, climate, and the management, how we apply the nutrients or how we manage that crop. And the fate of the applied nitrogen source is dictated by the source, the 4 R's. The source, are we using urea or UAN? The rate that we apply it at, the timing, are we split applying, are we spoon feeding? And the placement, are we putting it, through irrigation, or are we knifing it in, are we tilling it in, or are we surface applying urea in July when we have very high volatilization losses? So all of these factors confound optimum N rate so that it doesn't fall in a linear relationship with yield like the total nitrogen uptake does. And so Stanford captured this in a very simple model, that the fertilizer needed is equal to the plant nitrogen uptake or need minus what the soil gives us for free divided by the efficiency of the fertilizer. And so how much does the plant need? How much does the soil give me, typically from organic matter? And is the fertilizer efficiency, is the fertilizer efficiency or the percentage of the applied fertilizer that gets to the plant? If I use surface applied urea in the summertime, I might lose 40% to volatilization. So, I've got a factor of 60% there. And so we're basically trying to balance this, but the problem is we have to be able to predict soil supply and loss, and that's difficult. And we can get much more complicated. Stanford's original equation is rather simplistic, but when we look at the soil supply side, just the soil supply side, we have the available soil or inorganic nitrogen, the soil organic nitrogen, the crop residue nitrogen, manure residual organic nitrogen, and so forth. It starts to get pretty complicated. So Stanford's equation attempts to represent the nitrogen cycle as a mathematical formula that allows us to determine the optimum nitrogen rate. But it only provides a framework to evaluate different nitrogen recommendation systems. So we can look at how we decide on our rate and compare it to Stanford's equation and see which component it relies most heavily on. Ultimately, our ability to calculate nitrogen requirement will only be as good as our ability to estimate the components of that equation. So what are the size of the soil nitrogen pools? What is the rate and timing of transformations between those pools? How quickly will organic nitrogen applied with manure transform to nitrate and ammonia? The efficiency of the nitrogen supply from these different pools to the crop. And so there are models that help us to estimate this. And we see that that's what's developing on the industry side, is that there's multiple models that different companies sell to make nitrogen recommendations. You might have heard of DAPT-N that Cornell developed. It was recently purchased by Yara. You've got Encirca, you've got Climate View. There's multiple models out there that attempt to take weather models perhaps and soil models, and it may lean more heavily on one than the other, to fill in the missing parts of Stanford's equation. I'm going to move into talking about optical sensors now, because I've done most of my work with sensors. I'm not saying they're the only answer, but going forward here, the rest of this discussion, I want to use them as an example of how we can evaluate a more advanced process using an old model like Stanford's equation. So what is an optical sensor? For those that might not know, it's basically just a sensor that can be either handheld to get an average flat rate for the field, which basically just helps you adjust and give you temporally variable nitrogen, right? So you can change the rate each year by going out and sensing the crop each year and coming up with a different flat rate. Or it can be an equipment mounted sensor that gives feedback to your fertilizer controller and changes the rate probably every second as you travel across the field based on the reading. What is that reading? Well, the sensor emits light in or around the red and near infrared wavelengths. The different sensor companies might argue over they have a better wavelength than another. I don't think it really matters too much. I mean, once we get this all nailed down, we can worry about the minutia, but it's just important to understand that generally they're taking this average reflectance, probably calculating it every second. Maybe they're taking 60 readings per second and then averaging it per second. And then it's feeding information to a computer that converts that information into a nitrogen rate and changes the rate on the fly. Typically, we're using something like a simple ratio of just red to near infrared, or maybe it's something like the normalized differential vegetative index, or NDVI, that is near infrared minus red divided by near infrared plus red. And so NDVI has a very close correlation to total plant biomass, how much plant is above ground. In fact, it becomes difficult using NDVI later in the season because it saturates, because all the sensor sees is plant material, and so you get just a flat high NDVI reading. NDVI actually tells us something about how much plant it sees and how much soil it sees shining through. And so it gives you that biomass until the plant covers the whole view, and then it just saturates. Sensor readings can be related to crop vigor and nitrogen need using models or algorithms. So those models and plant response using reference strips in combination with sensors can kind of adapt your rate recommendation to growing conditions that occurred early in the season, and you can vary your rate spatially and temporally. Some sensor models address yield potential and nitrogen responsiveness independently. So we think back to those components that contribute to nitrogen requirement. Yield potential and nitrogen responsiveness are big ones. There are two distinct approaches to N rate calculations using sensors: the use of a yield prediction and response, or the use of response only. So response is thought of in two ways. The response index increases above is the increase above a standard pre-plant. So it's going to be greater than 1. It's called a response index, and what you have is a reference strip, and then that has high nitrogen applied at planting, and then the rest of the field. And that reference strip, if it's above the rest of the field, your response index is going to be greater than 1. So if you have a response index of 1.2, you expect an increase in yield of 20% with nitrogen. A sufficiency index looks at it the other way, and this was developed back when the first leaf chlorophyll meters were developed. And it's less than 1. And so again, you have a high nitrogen reference strip, and if the crop you're sensing is less than that, the sufficiency index will be less than 1. So sufficiency index of 0.75, the expected nitrogen need of 200, so you need to know what the expected need was, then the farmer practice is 150. So you can see a sufficiency index plotted here where the high nitrogen optimum is equal to 1, and anything below that we assume is nitrogen deficient. And we can calculate a sufficiency index or response index using the NDVI or the simple ratio. So what, a response index is what I'm going to talk about going forward, because this is the type of algorithm I've used, and we need a reference strip. So what is a reference strip? The Mid-Atlantic green seeker algorithm that Dr. Thomas and Dr. Phillips developed at Virginia Tech uses a low-end reference and a high-end reference. And here's a field with some work that we did in Maryland. You can see a big strip where the farmer at planting put a lot of extra nitrogen. You see that green spot in the foreground. And that's our low-end reference. And this crop is somewhere around V6. And so we can see that we have a response to nitrogen. We see that we lose color when there's no nitrogen applied in the starter. And the rest of the field just has a normal starter rate of about 50 pounds per acre applied with the planter, nitrogen. It can be anywhere in the field. You just want it to be representative, and you want to do it for each field. And so the response index is the ratio of the high reference area divided by the low reference area. So maybe you get an NDVI of 0.8 for the high reference and 0.4 for the low reference, and so your response index is 2. And then you get this algorithm that varies nitrogen rate based on yield potential and responsiveness. How do we do that? In this case, you're going to put the lower nitrogen rate on the poorest crop, somewhat lower nitrogen rate on the best area of the fields, and the highest rate in that intermediate area. The farmer would have applied a flat rate across all of those NDVI readings. So the algorithm predicts yield without side dress nitrogen. So it takes and says, what would the yield be, YPO, if I don't fertilize? And it uses that reference, that response index, the NDVI of the current plant you're looking at in the days from planting. And it's an exponential growth equation. And then the algorithm also has an equation that predicts yield with nitrogen. We're not going to worry about all these other coefficients. It's not necessary to get into the math. But that yield with nitrogen is the response index times the current plant you're looking at divided by days from planting. So you're basically saying, how much growth have I had every day up until now when I'm side dressing at V6? So maybe I'm 30 days into the season. And then I'm saying my response index in this case was 1.5, so I expect a 50% yield increase if I do fertilize. The user does have to supply a max yield for the field because these equations that predict yield are exponential and keep to increasing to unrealistic values. So the user says the most this field can do is 275 bushels per acre. The responsiveness is the difference between these two predictions. So we take YPN and subtract YPO from it. So the yield if I fertilize minus the yield if I don't fertilize. What is that difference? And it's doing this every second as you travel across the field. And then it takes that difference and multiplies it times the nitrogen concentration in the grain. So this is Stanford's equation, right? It's the nitrogen in the crop if I fertilize. So yield with fertilizer, yield without fertilizer. The yield without fertilizer is the nitrogen I'm getting from the soil because I'm taking the yield without fertilizer times the pounds of nitrogen per pound of grain. And so I'm getting how much nitrogen did the soil supply without fertilizer? How much nitrogen or how much yield would I get if I fertilize to sufficiency? The difference is the total amount of nitrogen I need to add over top of what the soil supplies. And I also have that NUE number. We typically keep it at 0.5 because we just don't have a good way to predict that. Here, the max yield replaces the yield with nitrogen because we say, well, that yield with nitrogen, as it goes up to unrealistic numbers, we can just say the yield unfertilized, the soil, that's why we go back down in the really good areas because the soil is supplying all the nitrogen that we need in those really good areas, the really extremely good areas. It's not unusual to see that typically the sensors operate in this range and only infrequently do we get up into this area. This is really a very good area of the field, and so it's a small percentage of the field. And so as you can see, we're varying it versus the standard practice of the farmer across that NDVI range in the field. So the question is, can we use models and other data layers and sensors together to improve this approach? Unfortunately, what happens in science is, there's people that developed algorithms for sensors. And they developed it and they did a great job and they wrote a lot of papers and it's been introduced in the marketplace. And then some other people went out and started working on models like whatever commercial model is available to you. And they made their model. But they don't tend to merge because it tends to be different companies that invest in these technologies. And the way I see it, we need to start bringing some of these technologies together because we can incorporate models and other layers to improve these sensors. Effectively, sensor algorithm technology hasn't changed in over 20 years. So we have this max yield number in place of unrealistic yield predictions. Can we just, that max yield is different for different areas of the field. So can we use historic yield maps to have a layer so that number changes as I travel across the field so it's not a static number the farmer entered? Or even can we go more advanced and come up with better crop yield prediction models that don't go up to those unrealistic numbers, but instead adjust spatially as we travel across the field? I think that technology exists, but it hasn't been integrated with the sensors. The nitrogen use efficiency number, and this number here, I didn't talk about it, but it's kind of what we think we need to jumpstart the system. And so we take the nitrogen pre-plant applied and subtract it from 100 kilograms per hectare of nitrogen, which is kind of what this algorithm determined locally was needed to jumpstart the system. And so, we've got to look at soil maps, climate models. These parameters likely vary in space and probably time, but I think that nitrogen use efficiency is often related to just soil texture or soil water holding capacity. And so can we adjust that based on a soil map instead of just putting in 0.5 because that's what we do? Also, the farmer has to put in basically restraints. Typically, we do this based on the pressure jump that his side dress unit can achieve. With new solenoid nozzles and better application equipment, Can we get rid of these parameters that we have to put in to limit it? Can we come up with guidance, better guidance on these limits? Really, this is just something that you learn through experience where to set those limits. Can we automate these limits so the farmer doesn't have to enter them? Because as you'll see, there's been pretty low adoption of this technology broadly across the US and globally. And so part of that has to do with the complexity of having to enter and the uncertainty that farmers feel with coming up with these limits and the NUE number and what is my max yield. If we can automate these things, I think we can increase adoption. So just a little bit about performance. This is data from Wade Thomason down at Virginia Tech when he verified his model, and over many field sites, he was reducing side dress N about 20% with no statistical difference in yield. Just because I like to harp on precision, here's some data from Maryland, 2010. We did for many years large field trials with this, with full nitrogen response trials in the field, and then using the green seeker sensor and Wade's algorithm. We saw an average reduction of 25%, so in line with what he found over the long term. But to be precise, it was different for each field site. So in that year, we had 7 field sites, and we had farmers that saw very little benefit with only a nitrogen savings of 5%. And then one farmer that we cut the rate by 50%. In that situation, I actually remember it. It was a manure field. We were following university guidance. The farmer practice was right to the T of university guidance using a PSNT. Very, progressive, a very restrictive nitrogen rate from that perspective. And yet, the sensor came in and said, no, this year you've had enough mineralization from historic applications, and it cut the rate way back and cut the side dress rate in half. So to be precise, there's a wide range of response, but on average, to be accurate, it's a 20 to 25% reduction using the technology as it stands today. So a couple of closing thoughts on nitrogen. First, I think it's apparent that we need a new mousetrap. We keep working around the edges. Environmental groups talking about how it's more economical for farmers to lower their nitrogen rates, that they're grossly over-applying beyond recommendations. I simply think that's not true. I think farmers are generally following some sort of professional guidance on the nitrogen rates, that the modern farmer is very conscious of the economics and the environmental impact. I think that implementing our current best management practices, while necessary, because they allow us to kick the can down the road, so cover crops, no-till, injecting fertilizer, split application, using more advanced tests in the current green seeker technology, all these things are necessary because they're putting off the inevitable. Without them, the current situation would be much worse in our waterways. But we need a new mousetrap if in the long term, we're going to be able to support a profitable farm and continue to decrease nitrogen inputs to the Mississippi River and other watersheds. Field research has repeatedly shown sensor-based variable rate nitrogen works. Implementation has been slow due to user confidence and perceived complexity. I would say we need to integrate across platforms and disciplines, bring the modelers in, and build a better model with the sensor. The sensor gives us real-time temporal data that can't be replaced. The models can look at the processes that occur within the soil or at climate processes and how they affect crop growth and soil processes. We also need to work on fertilizer technology. If we can develop better fertilizers with higher use efficiency, we can improve our confidence in the calculations we do with Stanford's equation. Remember, a big component of it on that denominator was fertilizer use efficiency. We need better application equipment. The full potential of sensors, whether it's the Optrix, the Yara sensor, the Green Seeker, can only be achieved if the equipment can deliver what the sensor's calling for. And so we need equipment that can deliver and vary the rates precisely in space and time as the computer is calling for that rate change. And this is a very difficult challenge, and it's one of the things that farmers who buy into this technology find to be the most frustrating, is getting the components to work together just from a mechanical side. So while we have all this research to do on the agronomic, soil, and climate side, the old-fashioned, metal benders, ag engineers, We need them involved, and we need computer engineers and electrical engineers working on better equipment. Improved models, I beat this one to death. Models are nothing more than a recommendation system. Even if your recommendation system says take your yield goal and multiply it by 1. So if you want to grow 180 bushels, put down 180 pounds of nitrogen, that's a model. That's Stanford's equation. And that technology has not changed, regardless of whether you're using MRTN, yield-based, or some other system, fundamentally hasn't changed much in 50 years. And finally, data management interpretation. Big data is all everyone wants to talk about, and I think it will play a role in this because it helps us to verify, to adapt, and improve technologies as they're implemented on the farm. So engineers, modelers, soil scientists, agronomists, farmers, economists, and social scientists need to collaborate across spatial, temporal, and philosophical scales. And that philosophical scale is important because we all talk different languages. And we need the social scientists because we need to understand decision-making and technology adoption. I harp on this one a lot. Variable rate nitrogen based on sensors has been verified in the scientific literature. It is a scientific proven technology, and yet I think in the marketplace, most people don't realize that. On the flip side, 70% of the phosphorus supply in the United States is varied in variable rate, and yet we don't have any scientifically verified mechanism for doing variable rate phosphorus to deliver that recommendation in a spatially variable way. It has not been demonstrated to work, and yet everyone's doing that. No one's doing variable rate nitrogen with sensors, and yet that's been demonstrated to work. We need to understand how farmers make decisions on adopting technology. So with that, I think I have used all of my time, and I think we have a few minutes left for questions, and you'll notice here in Kentucky, we only grow big blue corn.
Thank you, Josh. Yeah, we're fortunate to have you present today, yeah, very thankful. So we do have some time for Q&A, like you mentioned. So if the audience members, if you could take this time to answer or to submit your questions, I have a couple to get us started. So what makes a field not responsive to nitrogen? And is a field's responsiveness likely to change much from one year to the next?
Okay, what makes a field not responsive to nitrogen? You know, two big factors. One, there's an organic source that's mineralizing more nitrogen than we expect, or maybe it's how much we expected. And so we go in at side dress time, and we put out a strip of 0 pounds per acre and a strip with 100 pounds per acre of nitrogen, and the 0 pounds does as good as the 100 pounds. Well, that let's say we applied poultry litter, delivered more nitrogen. In that one case with a farmer, the green seeker cut back his rate 50%. That's what that was. There was poultry litter that mineralized more than university recommendations predicted. Our recommendations are an average, and it's very hard to predict organic mineralization because it's so climate dependent. The other factor that I think everyone's familiar with is drought. So if I have a very dry year, I get enough nitrogen to support a 30 bushel corn crop from my soil. 1% organic matter is going to give up 30 pounds or enough nitrogen to support 30 bushels. So I can grow 30 bushels without any added fertilizer in a drought year. Now, a farmer doesn't want 30 bushels per acre, but that is in fact a non-responsive site. And so using models and sensors, those two extreme opposites, because you've got this one situation with 200 bushel corn, and I didn't need to fertilize because I was getting it from the soil. The sensor combined with the model should be able to predict those situations.
Okay. Next question. Are you aware of any ag retailers offering nitrogen sensor-driven nitrogen applications as a service?
Yes. I'm not going to mention any names on a webinar, but yes, people that I talk to who are crop consultants, I've met crop consultants, and I know people in the retail industry that retail the sensors that say, I think it's very difficult. I have some good friends who are ag retailers back on the East Coast where I used to work at the University of Maryland before coming to Kentucky, and they bought some sensors and they could never figure out how to capitalize that product or how to price that fringe, right, of that benefit of varying rate. They just really struggled with it because of the way their business was set up. But on the flip side, I knew other retailers who were doing commercial applications, and they had clientele that would pay for the sensor. And so with the sensor, on average, you put down less. But actually, surprisingly, one of the things farmers get most concerned about that buy into this technology themselves is when it starts calling for more. And I get nervous phone calls where they say, I didn't budget for this, and it's saying I need more nitrogen in all my fields. So while I always focus, because on average, we do usually cut rate by spatially varying the rate, sometimes all your corn falls into that area where the rate needs to go up, you know, and that's a problem. But the retailers, some of them have figured out how to price for the technology versus the fertilizer.
Okay, great. So the next one. So some northern university test results have shown limited improvement in nitrogen management with sensors and have not been promoting sensors. Do sensors work better as you go further south? What are your thoughts?
I'm glad you put in the component about what are your thoughts, because this is the part where I get to opine on why some people see benefits from sensor technology. Obviously, I'm very high on it. All of our tests on the East Coast, we're getting ready to pursue it now in Kentucky, we're extremely successful. It doesn't work every time, but what standard do we hold it against? And so if we hold it against farmer practice, we always were able to excel, not always, in most cases, above 95% of the time, we were able to beat the standard flat rate practice. I won't even call it farmer practice, but compared against whatever they were doing. And the northern universities tend to work together, the Northern Corn Belt, and there are some distinct reasons why in corn I think the technology might not work. Some process kind of oriented things. Because of the cool weather and higher organic matter content, you tend to have soils that are not showing differences. The crop is not showing differences at the time you're side dressing. So when you go in between V6 and V10, which is about the right time to hit it with a sensor, you still have more than enough soil nitrogen to supply that crop because of your higher organic matter levels. And also it comes down to the algorithm. Different states have used different algorithms and different sensor technologies. And so a lot of the Northern Corn Belt relies on a sufficiency index approach, which is completely different than what I just presented. It does not include yield prediction and responsiveness. And they haven't developed a yield prediction equation, which has to be local at this point until we can improve models that are more robust, but you have to have a local yield prediction equation. And those universities that the questioner is asking about are using a different type of algorithm. They're not using responsiveness. They're not using yield prediction. But even if they were, I could see the challenge of those soils supply so much nitrogen, you're not seeing differences, so it's not going to really vary the rate as you travel across the field. So those are my I could talk about this all day long because I talk to my colleagues at the northern universities quite frequently about this. And I think it's the approach they use, it is their soils, it is their climate. So it's the combination of factors. And I think, you're going to have to figure out a better way to predict responsiveness on those soils that at V6 aren't showing their responsiveness, because the crop only needs about 20 pounds of nitrogen. If your organic matter is at 5%, you've got more than enough. And so, how do we go forward from there? Maybe models help them do better.
Okay. And the next question, so somebody said, great points. One thing missing from closing thoughts is the risk of not having enough nitrogen and weather prevents access when crop growing rapidly from V6 to V12. Operationally, neither service providers or farmers can cover all acres in a 2-week period. Who assumes risk?
That's absolutely right. This is a great question that we run into all the time. So to the first part about the, the closing point, the economic argument, that's right. I guess I try and keep my font pretty big on my slides. That's my only excuse. I have to limit my points, but you're absolutely right. And in other talks where I focus more on this, that 30-pound surplus above the economic optimal rate is really important. So there's a couple of studies that have been done where they did, and there are actually nitrogen response models, commercial models that include this in them. As one of their developers told me, it is their secret sauce in their model. to use stochastic risk assessment of the risk of under-fertilizing to build the rate. And so how heavily do we weight that risk? Because it costs more to be short than over-fertilize. Nitrogen is cheap, grain is expensive. If I am a pound low on nitrogen, I lose more money than if I'm a pound high. That's the economics of it. And then when we look at that precision, where I showed a couple slides on it, it amplifies that so that the right rate is 30 pounds higher than the economic optimum rate. Access is the second component of that, the reason that sensors limit in adoption, particularly in the big corn producing states, particularly where people are relying on the retailer for application and don't have their own equipment. One of the reasons I think adoption has been relatively good in the mid-Atlantic is because most of the people there, the bigger grain farmers, are doing their own side dress nitrogen applications and always have. As I moved to the Midwest, one of the things that was the biggest shock to me was the lack of side dress. 20 years ago or so, I mean, we still have large swaths of the Corn Belt that are doing fall application of anhydrous, right? Because the climate and the soils allow you to get away with it. I still don't think it's more efficient than split application in season, but you can get away with it economically. Back east, further south, you can't get away with it economically. You'd lose your shirt if you did that. And so there's plenty of equipment in those regions. There's a limited access to high clearance equipment that can side dress corn as we move further north and further west into the Corn Belt. And so that is a problem you can't get around. And so the sensor adoption, I always say, first figure out how to side dress and do that for 2 decades before you try and go into models and sensors. Because if you try and swallow the whole pill at once, it's like drinking out of a fire hose.
Okay, I think let's try to do one last question. What value can there be in a nitrogen model from a sales aspect to try to identify if we use too much nitrogen? Yellow corn causes growers to react, but green corn does not trigger a thought, oh no, we over-fertilized.
Right. So this is why you need economists and sociologists and maybe which one is the one that can give you drugs, psychiatrists or psychologists? Whichever one gives us drugs is probably the ones we need involved in agriculture, because this is how people respond to technology, and economists can tell us how to price this technology. You're selling something that should offset risk, right? Because right now, well, the way we offset risk right now is let's apply, above sufficiency so we never see yellow corn, and we're comfortable with that. But truly, we can run short in that situation depending on, climate events, heavy rain in the spring, whatever. And if we say we're coming up with better technologies to offset that risk, then we should be saying we're selling a technology that is less risky. But how is that perceived? That's why I'm not in business. If I knew how to sell this, I'd be selling it, right? But I don't. I do the research. And so I always say these things it takes time. That's why I don't wring my hands over slow adoption. I just think it has to run around out there in the wild, and the true entrepreneurs will figure out if it truly is better. I think the open market will say this is a better way. Forget the environment, forget external pressures. This is worth adopting because it truly does a better job, decreases my risk, lowers my input costs, and maintains or improves my yield. But it takes a long time for people to overcome their skepticism and fears. And in the marketplace, you got to figure out very complex things about how do you price for better advice versus more fertilizer, and how do you offset who assumes that risk if you do fall short. And so right now we just don't take any risk because we put these huge confidence intervals. The problem with precision ag, and I mentioned variable rate phosphorus for like 1 second. The problem with precision ag is it only works if we're working right around the sufficiency range. If we go grossly above and put these huge confidence intervals, so if the right rate's 100 pounds, so we go to 150, so we never run rate low, then precision ag is pointless. We're varying rates all above sufficiency. It's pointless. And that's what we see oftentimes with phosphorus and nitrogen. And it is risky to be moving rates around, chasing that right rate in the field, because you are going to miss the mark and fall short. And right now what we do is we just make sure we're above across the whole field.
Okay, great. Well, thank you, Josh. I guess in the interest of time, I'd like to wrap up the Q&A. So yeah, I want to thank Josh for joining us today. We really appreciate him taking the time.
I appreciate you guys having me.
Thank you. So I'm going to get my screen back up. So at this time, I want to recognize our participating ag retailers. If you're an ag retailer in the Great Lakes Basin that's interested in participating in this partnership to benefit your business and water quality, please contact our outreach coordinator, Caitlin Leahy, at caitlin@partnershipfarm.org. And finally, I'd like to acknowledge our funders, collaborators, and members that made this webinar possible. In particular, the support of the Great Lakes Protection Fund and the National Fish and Wildlife Foundation. We've also been enrolling corporate members to support our partnership, so we'd like to highlight our two most recent members, the Andersons and Garrett Ag Services. Their contribution helped make this webinar possible and helps to promote the strides that ag retailers like you are making to reduce nutrient impairments. If you're interested in becoming a member and receiving additional benefits included, please visit our website, partnershipfarm.org, to fill out our online form. And as we wrap up, please remember to look for the email later this afternoon with the webinar evaluation, webinar recording, and a link to submit your CCA credentials to earn the 1.5 CCA CEUs, and only if you've not already done so during registration. And so I want to thank you all again for joining us today, and I hope you will join us for our next webinar in June. Thank you.